Yeah, Dominic, I can see your slide. You're welcome to start. Thank you.
Yes, thank you, Saria. Thank you all the organizers, Scott, Daryl, Jess, for inviting me here. My name is Domenico Giardini. I've been trained as a theoretical physicist, but I'm actually a seismologist. I work on earthquakes. My usual cooperation in Canada is with the Canadian Geological Survey, which is they're your cousins, but they do something else. And I will show you how from there I got to LISA and what we do for LISA. My group is responsible for delivering the front-end electronics of the core of the sensors, which is the gravitational reference sensors. My co-author here is Luigi Ferraioli, is my chief electronic engineer. Now, the contents of my talk will be coming from Mars. I'll explain, and then what we achieved in LISA Pathfinder, what we achieved in LISA Overview, what we plan to achieve, and then the GRS plus the front-end electronics overview, the LISA schedule, milestones, the new schedule of LISA, which is very exciting, what we're doing in B1. And then I will spend a few minutes on why should Canada contribute, in the sense of contribute hardware to the mission, what could contribute, how, and when. Now, I do come from Mars. It's actually a fact, having installed seismometer all over the Earth, we also installed the seismometer with the NASA InSight mission on the surface of Mars. The seismometer is working since 3 years and is still running there. But when we were preparing this, we got a phone call from ESA, that's early in about 2001, when we were already working on designing this electronics. We got a phone call from ESA saying, oh, okay, you know, we have another mission that could use your class of very high precision space electronics. And they sent us a proposal for LISA that was in the phase of digestion by ESA at that time. And basically, I thank John for having shown what you can do with a set of 3 seismometers running in space. John gave a very exciting presentation. And LISA is technically extremely challenging, is the largest mission that ESA ever tried to send in space. But in the back is just a set of masses which are included in a couple of boxes, and that's what the seismometer is all about. And so the electronics that controls that is very high precision electronics, which is very similar to the one running on Mars. The LISA Pathfinder was launched in 2015-16. ESA did not really believe that we could reach the precision that we had claimed we could in terms of, let's say, fraction of picometers over a length of a couple of million miles. And so they launched a pre-mission, and the LISA Pathfinder taught us a lot and put us on a maturity level that allows to move relatively fast. The LISA Pathfinder principle was quite simple. You have your 2 masses, 40 centimeters from each other. In the middle, you have your entire optical bench with all the laser beam splitting and so on. That measures the distance. Of course, when you translate it into something that needs to fly, is a little bit more complicated the way it looks like. So have your 2 reference systems, reference sensors. The 2 masses are included inside these boxes that need to. They're full of sensors on the side, and they need to understand where the masses are so that the spacecraft can fly with the mass. And that's basically the core of a seismometer, if you like. A seismometer is built exactly like that, only it doesn't have all the rest to connect it. And once you have all of this ready, you have to fly it out. And this is your optical bench, your 2 masses out there, contained in the boxes, contained in the GRS, contained in the entire spacecraft. Now, for 2 masses of this tiny size, you have here around huge boxes of electronics that need to sense where the masses are and actuate the masses and actuate the spacecraft so that it follows the masses in such a way that the mass does not even know that there is a spacecraft around it. It just believes that it's flying in a Newtonian trajectory around the sun. And then, of course, you attach an engine, and then you pack the whole thing and you send it fly. In this case, it was in the Lagrangian point 1 for 2 years. Now, we gained a lot of knowledge out of this, which allows them to design LISA. LISA will be more complicated, has 2 masses, 60 degrees in each direction. And so the entire command that you need to give to each mass so that you can get good measures out of this triangular shape, it's little bit more complicated that we had in LISA Pathfinder. The sources of noise are different. The measuring principle is always the same. That is, you have two main points here that you need to control. One is how you measure the distance between two spacecrafts or between the two masses. And the other one is how you govern the spacecraft so that they can leave the masses undisturbed and follow the masses around the sun. So this is an overview, the exploded view of the MOSA. MOSA is the key, so the moving optical subsystem is what we deliver as a consortium. The rest belongs to the spacecraft, to ESA and the primes. There is a telescope with the laser beam, which is sent to, and then the telescope protection. Then there is an optical bench. In the back, you have your GRS, so your gravitational reference sensors with the mass inside. There is a single mass in each one of them. And then all of this is what constitutes your MOSA. The MOSA is the one that was shown here that points toward the other mass. So the total of this is our MOSA. And then, of course, the mass is inside. And what we want is, of course, to fly the whole thing. And then it immediately becomes more complicated. So my presentation will drive you away from what you can do with the data once you collect them, but how do you actually mount a mission so that it can collect the data that you need to do everything that John was showing before. So this is just the MOSA part with all the various elements, who delivers what where. When you read ESA, of course, is an industrial prime. Then you have the part coming from NASA, the laser, the telescope. Then you have the part coming for the GRS. That means that the core of the sensor that has the mass and measures where the mass is and steers the spacecraft to follow the mass. And then you have the entire optical part. You see that there are many flags here. And my presentation today will be, in the end, on how to include also the Canadian flag here. This, by the way, is the electronics that we deliver for the LISA Pathfinder. It doesn't seem like, and I don't want to count electronics in terms of potatoes, but in the end, for LISA, we are expected to deliver a little bit above 240 kilos of space-qualified electronics. So in the end, that's where the complexity of all of this comes. The electronics has to work. Many of you are working already in the consortium. The consortium includes a number of expert groups, a number of teams. There are work package teams, there are instruments team, data challenge, astrophysics, cosmology, fundamental physics. I, for example, have a group working in the LISA data challenge because we are expert in waveforms, wherever the waveforms come from. And so we're very interested in extracting waveform from noise, and we want to know how we will perform once we fly. And in addition, we have a number of governance committees, diversity, equity, and inclusion. So everything that you would have that connects to what Jess was showing at the beginning, that the committee, that the entire consortium, this is more than 1,500 people today, the consortium behaves as it should be behaving. Where I'm sitting myself, I'm sitting in the executive committee here with all the main PIs of the main systems and subsystems. It's a group of 6, which involves also a colleague from MIT, from NASA, and 5 Europeans. And so that's where a lot of the decisions are taken. Now, what we learned from and what we bring to LISA and what we learn in LISA Pathfinder are the top science requirements. We could demonstrate that we actually could reach 2 femtometer per square second per square root of Earth. Originally, the Pathfinder requirements were this. The units are here on the side. For expected LISA requirement like this. And actually, we reached much better than the LISA requirement already in the first Pathfinder. So that's what actually convinced ESA, in addition to the LIGO observations. Then the science mode, the capacity position sensing, the electrostatic force actuators, we could show that we could move masses and the spacecraft with accelerations which are equivalent to 10 to the minus 15 g, and that's what is required then for LISA. And then survive launch, release into free fall. So all of this was demonstrated by Pathfinder. Pathfinder, however, had something else. When we sum up, and that's one of the main activity now, all the noise sources that we can quantify to understand what we measure in Pathfinder, we still at low frequency, between tenths of a millihertz and a millihertz. We have sources of noise and glitches that we haven't explained yet. And of course, you do need to explain all of this to avoid surprises when you find LISA. If you don't explain the low frequency, you will miss some of what John was showing before. So in phase A and B1 for LISA, what we are delivering is the delta design coming from the Pathfinder going to LISA, the full exploration of the entire 31 sources of noise identified for LISA. We do the performance analysis, the testing upgrade to move to LISA. Now, let me move to the GRS. The GRS, the head, that means Italy delivers the hardware for the GRS, including all the mechanical system that cage the mass during launch and flight, that open it to space. There is a lot of LPF heritage. LPF stands for LISA Pathfinder. Then all the mechanical systems that govern the mass are again delivered yet now by Italy. Originally, they were in Swiss industry. The front-end electronics is done in Switzerland, and the charge mechanism, the pulsed UV that serve to charge and discharge the mass is delivered by NASA. The system is a double system. It has on both, for the two channels going out from one spacecraft, you have your mass, the second mass, the mechanical units, electronics, and the charging systems. And in between, you have everything that connects so that the spacecraft knows to whom to obey, which mass to follow, and how to steer one of the masses or actuate one of the masses so that it doesn't touch the box in which it is contained. The front-end electronics has a scheme like this, and I will not enter into detail, but just to explain that you always see all the system, there is an N, which is a nominal, and R, which is a redundant. We do have all these systems are redundant in order that if one fails, you activate the second. These give commands to the mass in terms of actuation, give command to the spacecraft in terms of actuation, and receives the timing and receives an exchange with the onboard computing all the data that they need. I do apologize, all these figures is not my fault. They have lots of acronyms. To understand all these acronyms takes time. You will be pleased to know that we do have an acronym set of, as you say, vocabulary of acronyms is 16 pages. So learning by memory is not obvious, but that's what you need here. The two main things we deliver are the sensing and actuation units and the power conditioning units. This is electronics as is best. We need to sense where the mass is with a precision of 200 micrometers in order, and we need then to steer everything else so that it flies with the mass and the mass is undisturbed. And basically, in order to do that, we need extremely high precision on the power, both the power for the waveforms, so the amplitude modulated, and both the power for the zero level, whatever level we have, so that every measure that comes out of here is extremely precise. And so the power conditioning units are at a precision that does not exist on Earth, but can be flown then in space. This is our product tree. The GRS-FEE is the total of it, and then we have the SAU, which is the sensing and actuation unit with all these various parts. It has, in the end, 3 analog units that control the 3 axes, because of course it's a cube and we have the 3 axes of control. Then we have the power conditioning, and then all the harnesses that they need to link in terms of cable and everything else to the spacecraft, either the MOSA or the spacecraft. Now, we have a new LISA schedule. Until June of this year, LISA was slipping away because it was a so-called L3 mission for ESA. It was supposed to be launched a few years after the X-ray telescope Athena. There was an L2 mission, but Athena was delaying more and more because of technical reasons. And so ESA cannot afford to have 2 large class missions on top of each other. And so we were delaying also LISA. This has now changed. Athena has now been instructed to redesign, and to descope in order to meet both technical targets and budget targets, and the mission adoption will be delayed. And they have anticipated the mission adoption of LISA to November 23 with a target launch of end 34 to beginning 35. For mission adoption, payload platform hardware must be at TRL level 5-6. The system design must be mature. The cost at completion forecast must fit within the science program, which is the one approved by all our governments. The documents that we need before mission adoption are the science management plan, the multilateral agreement that's signed by each country stating what they support, the memorandum of understanding with all the countries which are not part of ESA, for example, NASA, and the design definition reports. These are standard documents required for mission adoption, but now we're running because this mission adoption has been anticipated. Just to give you a feeling of what we need to deliver, and sorry again for the language, we will deliver basically one major EM, that's an electronic model that you do it at the start in order to prove that you can reach your capability, but this is not made with space qualified electronics or components, it's made with their components with the same type of again qualifications. Then the QM is a qualification model. This is already something that could fly. It's built with the same components and design as the flight models, will be used for assembly and testing of the GRS flight model, because otherwise the schedule would be too long. We wouldn't be able to fly in 2034. And then we deliver 6 flight models for the 6 masses and 1 flight spare. Possibly NASA, possibly ESA will request 2 flight spare. These are the ones that you replace even in the last days before launch in case something goes wrong. That's a schedule, only up to 2031. What you show here is different colors, the production of electronic model, qualification model, flight models. The schedule is something very complicated. We need to firm it up in time for the mission adoption that is about 1 year from now. It's going to be November next year. All the documents and the technology readiness assessment needs to be carried out by April next year, so let's say May, June next year, by spring next year. So things are running very fast. We are working at full speed on all of that. To be understood here is that's what you call phase B1. No, in a standard mission, you would deliver an electronic model in phase B1, but here the political decision, if or not, ESA will confirm the mission, adopt the mission, and confirm the launch date has to come before. We cannot wait for the electronic model that will be produced afterwards. And very important, it's also for the electronics, the delay time. All of you that work in electronics will know that the long lead items or standard EEE components that used to be delivered in 6 to 12 months, now everything goes into 12 to 24 months, depending on what you're waiting for. And so that adds delays, which we don't control. These are all elements that come, components that come from Taiwan or Korea or other countries, and we need to wait until they deliver them. I will not describe all of this. This is what we are doing in phase B1 and what we need to do in order to bring what we have done in LISA Pathfinder to be ready for LISA. And that's what we're working on together with our industry partners. Let me now bring you to why should Canada contribute and what could be contributed here. If I come to the product tree, the overview of the front-end electronics that I showed before, we have been discussing with partners and with your Canadian Space Agency a first model in which you would contribute, the Canadian industry would contribute to the power conditioning unit. That is a very important unit. There's not just power supply. From the precision of all of this, I will show you a few slides on that to depend how well you can do your sensing measures. And this could be built to spec. That means that the specifications come from the prime, both our prime industry and the prime of the mission at ESA. And then it would be designed by the Canadian industry. A second component would be part of the sensing and actuation units, and apart from the entire analog electronics, but part of the rest. And this would need to be built to print. That means the specifications are already defined from the LISA Pathfinder. They can only be modified very slightly. Otherwise, they would take too long to actually go back to it. Now, couple of things to explain why this is so critical. The entire power, the quality of the power that is provided is critical for the sensing and actuation. Unless the power is fully controlled, you don't reach the precision that are needed. And so provide condition power, provide high voltage supply are two of the this is everything that runs in the back so that you can take the measures. And unless this is fully stabilized and fully controlled, the measures just don't come out, or they come out more noisy. For the reference unit function is the same. This is part of the SAU, and the reference unit function provides the reference against which everything is measured and everything is moved. And so the stable voltage, the average voltage that you need for the amplitude modulated, capacitive sensitive, all of this comes from there. I have a few examples of this. This is what we are discussing presently and showing to your Canadian Space Agency to see what would be the interest of the Canadian industry to contribute to all of this. Now, the key thing, of course, is that your flag would be on the map after that. So there would be design authority on the entire PCU, on the power supply that would be with Canada, and joint design authority on the SAU, and shared design authority depending on which piece on the harnesses, harnesses cabling and all the connectors that you need to do that. It's important to look at the schedule. The schedule has been now anticipated, and so this is an enlargement of the same schedule that I showed before. The commitment of Canada would be required by mission adoption. Mission adoption is this one here in the fourth quarter, but we do need to provide to ESA a clear statement where Switzerland and Canada say what they cover. They don't have to cover it yet. They need to commit to what they will cover in the future. And since this is going to be in November next year, this commitment would need to come by end of spring next year. The EM, because of the time scale, we need to order by January next year the long lead items and so on. So the EM will be designed and commissioned by Switzerland. There is no way to bring in additional partners, but we would certainly wish participation on Canada in the EM in this phase when we start assembling the EM, which is in 2024. We would wish to have Canadian partners, the industry, especially with our industry, and that would be needed so that Canada can take some ownership in the design of the EM, which will then would transfer in the QM and FM that is in the flight models. The full participation of Canada has to be there latest by end of 2024, when all the commissioning for the qualification model, which has the same components as the flight models, comes out. So the commitment has to come early. Partial participation would have to come during 24 and full participation by end 24. This is the schedule that we have in mind. Which brings, of course, the question, why should Canada contribute LISA hardware? This is my last slide, which is the question that very often my school asked me, why don't you just wait for the data and download the data and get PhDs to work with the data when the data arrive? Because if we all do like this, of course, the missions will never fly. So we do have an obvious fact. If you participate from inside, you have a really true participation. In all phases of LISA, you sit in all the consortia, you sit in the decision, in designing the specs, in discussing with the agencies what you can do and what not. It's a different participation than just the science. Because Canada is one of the few countries that really can do it, can take up a major engagement. Of course, if you take it here, you don't take it someplace else, but you can and you should contribute to top missions of ESA. You are associated to ESA. It will provide a much better understanding of LISA data and its limitations. This, we learn it in every mission we do. If you are inside and you know the various steps and understand how the data collected, you will be able to react. I go back to the first slide that I showed on Mars. The teams that participated in installing the seismometer on Mars are the ones that get the better share of the science in the end, because we understand how those data are collected and what they show and their weaknesses and power. The planning for post-LISA instruments is already started, it's full swing. If you are inside LISA, you would be better positioned to play a role in there. Of course, it will help also with the ET or other terrestrial observatories for gravitational waves, because in the end, we're measuring strains. So understanding exactly what you need to do that would help also with the other experiments. And then these are developments that have important potential also for industrial return. my example is clear. We started working to bring a seismometer to Mars, which in the end it works with NASA on the seismometer and Elysium Planitia, but then we got cold, and then we delivered the same electronics for LPF and LISA. And now we have a number of European projects with leading industry partners in Europe, like Airbus and so on, to develop high precision electronics for space navigation. So once you control electronics to this level of precision, things then can be used for many other missions and many other applications. With that, I'd like to thank you all for the attention, and I'm finished with my presentation.
Thank you, Domenico, for the interesting and informative talk. Lots of things to think about. We are running a few minutes over time, but Domenico's talk started a couple of minutes late as well. So there's excellent questions in the chat, and I see a lot of them being answered. If there's a quick question, I'll let one quick question in a minute or like for so. Are there any questions, Domenico? Okay. If not, yes.
I've got a quick question.
Yes, please.
So if, I don't know how quick it is, but if, to play devil's advocate, if everyone participates in I'm an undergrad, so I'm a little bit new to the game, but these large projects, if everybody wants in on the project, is there a risk of like too many cooks in the kitchen? Like you're actually making it less efficient by having too many people?
Yes, it's a good question, but this is a very complex mission. The complexity comes from the fact that you need to deliver 3 spacecraft identical, all working in the same way with 6 units. And the industry, it's up to here for the complexity of what they need to deliver. As I said, this is the largest mission ever attempted by ESA. And 1/3 of it belongs to NASA exactly for this reason. And so this interplay between partners is already there. It's just at the moment, we only have 1 or 2 units which are not allocated. The rest is already defined. So we could sign a multilateral agreement for 90% of the mission by Christmas. We just need to do the final allocation for part of the FEE, plus an additional module in the optical bench, in the electronic the optical bench. For the rest is already all done. All those flags that you saw before in one of the, when I showed the entire MOSA, the flags are already assigned. So you cannot come in and say, oh, I'd like to do that. That's too late. Also because there is a lot of heritage from a mission that already flew. So the people that flew the early mission are there.
Okay. So if, so our participation wouldn't complicate the mission.
Depends how good your partners or industry are. That might be things, but
I guess so. Yeah.
You know, what we know, it would not. It would actually help.
Yeah. Okay. Awesome.
Yeah.
Okay,
thank you. Thank you for the question, and thanks for the answer. There are lots of good questions and discussion going on in the chat. Please continue doing that. I'd like to thank all the 3 speakers of this session. So thank you very much, and thanks to the attendees as well. We'll start the next session in about 9 minutes, 20 past the hour. Sorry for